இருக்கணும், என் ப்ரொடியூசரும் நன்றா இருக்கணும்.
Hello, good afternoon. I hope you can hear me.
Yes, sir.
Yes?
Yes, sir.
Okay, good. So let's start. I'm using this new technology today. Let me see if it works for you, whether you can follow what I'm doing. If there is any problem, just say so. Okay. So we have fixed a prime number P. And suppose we are given a polynomial f with coefficients in Zp. We have defined the ring Zp of periodic integers, right? And we are given a polynomial f with coefficients in Zp, and we want to find a root of this polynomial. Okay. Now, what does it mean for some psi to be a root of f? It means that this, see, if this psi is equal to psi n, right? And where psi n is in what? It's in z modulo p to the nz. So for psi to be a root of f, what you require is that these psi n, which is in z modulo p to the nz, should be a root of fn, where fn is the image of f in an. An is my abbreviation for z modulo p to the nz, right? So I'm not saying anything deep or difficult. I'm saying something which is obvious. So if psi is a root of zeta of f, then its image in an will be a root of the image of f. So giving psi, of course, is equivalent to giving these psi n for every n, but these psi n's should be compatible in the sense that psi n plus 1 should be congruent to psi n modulo p to the n. Okay. So that's what it means for psi to be a root of f. If psi is equal to this, then this psi n should be a root of fn for every n. And of course, psi n plus 1 should be equal to should be congruent to psi n modulo p to the n. In any case, so this shows that a necessary condition for there to be a root psi is that f1 should have a root psi 1 in the field fp. Okay. So for there to be a root x naught, f of x naught should be at least divisible by p. See, a root of f is some x naught, such that f of x naught is divisible by p squared, by p cubed, and so on. Because the only periodic number which is divisible by p squared, p cubed, and so on is the number 0. So a necessary condition for a root to exist is that there should be an x naught such that f of x naught is equal to 0. Okay. Now, suppose I have such a thing. I have an x naught such that f of x naught is equal to 0. Not equal to 0, it's congruent to 0 modulo p. If it's equal to 0, I found my root. There's nothing to do. I'm trying to find a root. And so suppose I have found something such that f of x naught is divisible by p. F of x naught is congruent to 0 modulo p. Then I want to improve it to an x1, which is not only congruent to 0 mod p, such that f of x1 should be congruent to 0 mod p squared. Ultimately, I'm looking for a number such that f of that number is divisible by p, p squared, p cubed, and so on. I'm trying to do it in steps. Suppose I have some x naught, which is congruent to 0 mod p, which is divisible by p. Then I'm going to find an x1, which is such that f of x1 is divisible by p squared. Okay, how do I find this x1? Now, so I'll try to find x1 because I want my x1 to be congruent to x naught modulo p. X1 will have to be of the form f of, it will have to be of the form x naught plus z1 times p. Okay, for some z1 which is in zp. Now for such an x1, how do you compute f of x1? For this you use this polynomial identity. This is something that you need to check. What is it? It says something very simple. I'm sure all of you will be able to check it for yourselves. What it says is that if I have a polynomial f, then f of t plus s is equal to f of t plus f prime of t. F prime is the formal derivative, right? This is the formal derivative. So f of t plus s is equal to f of t plus f prime of t times s plus some polynomial, I don't care what that polynomial is, times s squared. I request you to check it. This is very easy. You can use, for example, the fact that the derivative is a linear thing. The derivative of a sum is the sum of the derivatives, and so on. And every polynomial is a sum of some kind of monomials. So you just need to check it for monomials for which it is trivial. Okay. Now, so I'll use this identity to evaluate f of x1. So f of x1 will be, if I apply this identity, then I'll get f of x1 equal to f of x naught plus f prime of x naught times z1p. So here z1p is my s and this is my t and so on. So I'll get this. But f of x naught itself is y naught times p. Why is that? That's because f of x1, no, that's because f of x naught is here. It's congruent to 0 mod p, so it's divisible by p. So it's y naught times p for some y naught in zp. Okay, so when I put these two things together, what I get is that f of x1 is going to be congruent to 0 mod p squared if and only if this y naught plus f prime x naught times z1 is congruent to 0 mod p. Okay, so this is just from the basic properties of these things. Now look at what happens if there's an if here. If f prime of x naught is not congruent to 0 mod p, and something not being congruent to 0 mod p is the same thing as being invertible in zp, right? So if f prime of x naught is invertible, then I can take z1 here. I can solve for, see, z1 is what I was looking for. So I can take z1 to be this. Then I'll take my x1 to be x naught plus z1 times p, but that turns out to be this, because z1 is equal to this. And then you check that f of x1 is going to be congruent to 0 modulo p squared, and x1 is going to be congruent to x naught modulo p. Okay. So what this says is that if I have a simple root in zp modulo pzp, which is fp, right? This is the same as fp. If I have a simple root, what does simple mean? It's a root. So here it's a root, but this x naught is not a root of the derivative. Here is where we have used this. It's not a root of the derivative. I'll circle it in red if you want. Here, if f prime of x naught is not equal to 0, then we have defined this x1. So if we have a simple root, then we can uniquely lift it to a root of f in A2. We have a root in A1. What we want is a root in A1, a root in A2, a root in A3, such that these things map to each other, right? So we are starting with an x naught, which is a root here. Then we are improving it to an A1, which is to an x1, which is a root here, and so on, and which goes to this x naught, right? So that is the idea. You start with an x naught in A1, then we try to get an x1 in A2. I'm saying if your root x naught is simple, then you can take x1 to be this. Then it's a root here in A2 and so on, and it's congruent to x naught modulo p. x1 goes to x naught. Okay, so all this happens if your root x naught is simple. So I hope you have understood this, because this is the basic of this is the idea behind the following lemma. Okay, so here it says so. So this process can be iterated because of this condition. Because of this condition. Sorry, is somebody saying something? No, I can't hear anything. So we'll continue.
Please go on.
Okay. So this is the summary of what we have done. But if f prime of x1 is not congruent to 0 mod p, earlier we were using the condition f prime of x naught is not congruent to 0 mod p, right? That was x naught. Here I'm using the condition for x1. If that happens to be the case, then I can find an x2. I can repeat the same thing. I'll put x2 equal to x1 minus f of x1 divided by f prime of x1, just as here x1 was x0 minus this thing, right? So if I put x2 equal to this, then I can check these things easily. Okay, so if the first step was possible because of this, and the second step is possible because the x1 that I get will have this property that f prime of x1 is not going to be 0. Anyways, so that's the idea behind the proof of the following the result, which is called Hensel's lemma. Hensel's lemma. Okay. So what does it say? It says that suppose I have a polynomial f with coefficients in Zp, and I have a periodic number x0. Then of course I have the value of the polynomial and the value of the polynomial at x0 and the value of its derivative at x0. And then I have the valuations of these values. So what's the valuation? You remember what Vp was? It was a map from Zp to n union plus infinity. So VP of 0 was plus infinity. And if x is not equal to 0, then you write x as p to the m times some u, where u is in zp star, and vp of x is this m here. Okay, so that's the periodic valuation. So I'm taking m and delta to be the periodic valuations of f of x naught and f prime of x naught, right? And here is the hypothesis that m is strictly greater than 2 delta. If this holds, then there exists a psi in ZP such that f of psi is 0. So it's a root. It's a root of f. And moreover, this psi is congruent to the given x naught modulo p to the m minus delta. And finally, the VP of f prime of psi is equal to delta. So basically what is being said is that if this m and delta satisfy this simple condition that m is strictly greater than 2 delta, then there's a root of f which is congruent to x naught modulo p to the m minus delta, and whose the valuation of its value at the derivative is delta. Okay, so there's a statement, and here's the proof. So first of all, f prime of x naught is equal to p to the delta times u for some unit. Why is that? That this is what I recall. That's the definition of VP. And therefore, what is f of x naught? F of x naught, the valuation is m, which is bigger than delta. So the valuation of this is m, the valuation of this is delta. So the valuation of the quotient is m minus delta. That's VP. So m minus delta is of course strictly positive, because in fact m minus 2 delta is strictly positive. So which means that this thing is in ZP. Okay, and therefore because and this we have proved just now. Now we claim that f of x1 is to the x1. M is equal to VP of f of x naught. What does this mean? It means that f of x naught, it implies that this is equal to, this f of x naught is congruent to 0 modulo p to the m. So what is this now? What is the noise? Hello, where is the noise coming from?
Mute yourself.
Okay, right. Okay, I'm sorry, I didn't read the... So is it better now? Can you read the things better?
Yes.
Oh, okay, good. Sorry, I was not looking at the chat because in my iPad, I can't see the chats. It's there on the desktop. Anyway, so I hope you can see things better now. Okay, so these are the claims. X1 has been defined like this, and these claims are being made about this fx1. So this is the checking that these things actually hold. F of x1 is congruent to 0 modulo p to the m plus 1. It's checked here, for example, right? So what has been used? So that polynomial identity has been used here. Which polynomial identity? This one. This polynomial identity has been used, and because x1 is going to be written as, of course, x1 is equal to whatever x1 has been defined as. It's here, right? Let me put it in black. X1 has been, is the sum of two things, and therefore it's x0 minus f of x1, f of x0 divided by f prime of x0. Okay, so I get f of x1 congruent to 0 modulo p to the m plus 1. Now we'll apply that polynomial identity to f prime. Again, x1, you write your x1 as x0 plus x1 minus x0, and f prime of this is going to be f prime of x0 plus something else which I'm not interested in. Okay, so this shows that VP of f prime of x, VP of f prime of x is equal to VP of f prime of x0, which is delta by definition. So what are the claims about x1 that we wanted to prove? First of all, that f of x1 is congruent to 0 modulo p to the m plus 1, and we have established it here. Then we wanted to show that x VP of f prime of x1 is delta, and we have shown it here, right? So
here this f is monic or any polynomial?
f doesn't have to be monic, no. But right, I mean, it's an arbitrary polynomial. Where do you need it to be monic, for example?
Okay.
Yeah. It should work for an arbitrary polynomial.
So this says like given any polynomial, I can cook up a root in ZP.
Well, you have to start somewhere. No, given any polynomial.
Yeah, I am assuming some conditions that you have written x0 is in ZP, and those conditions are satisfying.
Right. I don't know what this thing is doing here. Anyway, yeah, you are right. So you have to start with an x0, and such that m and delta satisfy these conditions. Yeah. If you have such a x0, then you can improve it step by step to an actual root. That is what Hensel's lemma says. Now, those of you who are familiar with what is called Newton's method, or Newton's method for finding roots of real polynomials, this is somewhat analogous to Newton's method. Because that also, I mean, I believe that there also you take, you define the iterations to be something like this, right? Minus f of x naught divided by f of f prime of x. This is the basic thing. So here maybe it should be xn, and no, this is not what I wanted to do. I want this, yeah, here. Okay, so xn now, yeah. Okay, so let me do it again. What I wanted to write is, goodness, n plus 1 is equal to xn minus f of xn divided by f prime of xn. This is the iteration that you do in Newton's method as well. And this is exactly the iteration that we are doing here. F of x1 is, where is it? Here, for example, and so on, right? Okay, so this is Hensel's lemma, and then the proof ends here. This is the one which, this is about the uniqueness, perhaps. Okay, so now I come to some notation. So this group of units is called, I'll just abbreviate it to U, ZP star. These elements of this group are called units of ZP, and I'll simply write U for the units. Now for this kind of fields, for p-adic fields, everything comes with a filtration. So for example, the units U, inside this, there's going to be a subgroup U1. Inside this, there's going to be a subgroup U2. Inside this, there's a subgroup U3, and so on. So what are these UNs? What are these? What is this filtration? So U is the kernel. So U is, or let me just define UN. That's the kernel of the map pi n, which of course goes from, think of it as a map from ZP star to AN star, right? I have a map from ZP to AN. This is a morphism of rings. I'm calling it, we had called it pi n. So when I restrict it to the units, these units are contained in ZP, of course, and these units are contained here. So I get a restriction pi n here. So this is the map pi n. And of course, the kernel of this map is called UN. Now, why is UN plus 1 contained in UN? That's because let me see if I have space here. Yeah, that's because I have my Z. What was this? I have my ZP here, AN plus 1 here, AN here, and this is pi n, and this is pi n plus 1. And this was called Fn or something, whatever. But the thing is, this diagram commutes. So if something belongs to UN plus 1, if X here belongs to UN plus 1, it means that this X goes to 1 here. And because the diagram commutes, it has to go to 1 here as well, because this 1, of course, goes to 1, right? So basically, you have this U, which is ZP star, all units, they contain U1, which is a subgroup, and it consists of units of the form 1 plus P times A, where A is an arbitrary element in ZP. Similarly, this UN will consist of elements of the form 1 plus P to the N times A, where A is in ZP. Okay, so you have these groups of higher units, as they are called. Okay, now U modulo UN is AN star. Now, why is that? That's more or less by definition. because you have this map from U to AN star, right? That was the map by N, and the kernel of this map is, of course, UN by definition. And this is surjective. This pi n is surjective. That is why, because of this short exact sequence, this is this modulo this. So that's what gives you this. And in fact, for every R, you can look at UN modulo UN plus R. You can look at this. So that is going to be, there's going to be a short exact sequence like this. Okay, so in particular, if I take, I mean, in this sequence, you have this. If I take the case R equals, you take S equal to R plus 1 and take N equal to 1 in this sequence, so you'll get this short exact sequence. Okay, so we want to study these groups of units and higher units. So one of the things that we would like to determine is what is the set of squares in ZP star. That's a group, it's a commutative group, and you can multiply two elements. An element multiplied by itself is called a square, right? And you want to determine the set of all squares in this group. Okay. So before I do it, let me just see whether you all know, for example, what is FP. If I, instead of ZP star, I had FP star. What is the set of squares here? So
1 square, 2 square.
That's right. But is it a subgroup? And what's the index of this subgroup?
It's 2.
The index is 2, right? So that is the, we want to find out what, for example, is the index or a criterion for an element here to be a square. In ZP star, we want to give a criterion for an element to be a square. So for that, I need some terminology. And the first word I want to use is quadratic character. So that makes sense for any group whatsoever. Okay, and it is just a surjective homomorphism from G to Z star. Now, what is this Z star? You might wonder. It's, for me, Z star is just the group consisting of +1 and -1. And why do I call it Z star? Because if I have a ring A, then I have the group of its units. And the group of units of Z star, Z is a ring. So I can talk of the group of units of Z, and that turns out to be just equal to +1 and -1. Okay. What has happened? How do I get rid of this? I mean, there was something that happened.
You just push it on the right.
I push
That's
it left.
like, yeah.
Wonderful. Why didn't you tell me earlier? Okay, good. So, okay, so that's what a quadratic character is. A quadratic character is just a surjective homomorphism of groups from G to Z star. Right? Now, if P is an odd prime, our prime P is fixed. If it is odd, then this group is cyclic of even order. It's cyclic of order P -1. So it is a unique quadratic character. I'm going to call it lambda P. Here we said we know we want to determine the squares in FP star. Determine the squares are anyway. So does everybody agree that FP star has a unique quadratic character? I'm just calling it lambda p. Usually people denote it by a notation like this. And they call it Legendre symbol. Right? So if you're familiar with those things, that's fine. If you're not familiar with the Legendre symbol, that's also fine, because I'm defining it for you. I'm saying whenever I have a cyclic group C of even order, finite cyclic, right? Then it has a unique quadratic character. I mean, this is from the very definition, more or less. Okay, so this lambda p is a quadratic character of FP star. I'm going to consider it as a quadratic character of ZP star. How do I do that? I just take ZP star. I take the surjection to FP star, and then I apply this lambda p that goes to Z star, and this whole thing I just call it lambda p again. Okay, so I get a quadratic character of ZP star. Now that's very, very important. It's a very important quadratic character. We are basically setting up notation, right? Okay. Now, at some point I had the hypothesis that the prime p is odd. What happens if p is 2? Then let's first recall that this group Z modulo 4Z star, that consists of +1 and -1, right? It's a group of order 2. This is also a group of order 2. So there's a unique bijection. Lambda 4 is the bijection from here to here. And so lambda 4 is a quadratic character of Z modulo 4Z star, and therefore I can consider it as a quadratic character of Z mod Z2 star as well, because from Z2 star I have this surjection to Z mod 4Z star. Okay. Similarly, I have this is a group of order 2. This is a group of order 2. So I have this isomorphism lambda 8. Oh, what did I do? Something unexpected happened, but it doesn't matter. So lambda 8 plus is this isomorphism. That's the name I'm giving to this isomorphism. So now lambda 8 plus, that's I can think of it as a map from Z2 star to Z mod 8Z star to Z mod 8Z star modulo Z star. You know, Z star is also a subgroup of this. Z star is just +-1. So I can think of +-1 as a subgroup here. And this goes to Z star, and this whole thing is lambda 8 plus. Okay, so these notations will be used constantly. Okay, so now I have a criterion for a unit to be a square. It's a square if and only if lambda p of that unit is equal to +1. Of course, p is an odd prime. true. Otherwise, lambda p doesn't make sense. Lambda p has been defined only for p odd. For p equal to 2, what I've defined are lambda 4 and lambda 8 plus. I've defined these two things. These are quadratic. So this is a quadratic character of ZP star. These are also quadratic characters, but of Z2 star. Here P is odd. Okay, so let's come back to the statement here. It says that if P is an odd prime, then a unit in ZP star is a square if and only if lambda P of that unit is equal to +1. So it's an if and only if statement. One implication is easy, because if I have a square, then lambda P of that x squared is +1, because well, that's absolutely clear, right? Because I have lambda P of x squared is going to be lambda P of x squared, but that's equal to 1, because every square in Z star, the square of everything in Z star is equal to 1. So that implication is very easy. Is the reverse direction. Suppose I have this, then I want to show that U is a square. So suppose lambda P of U is equal to +1. What does that mean? That means that there's some x in ZP which is a root of this polynomial, such that, you see, lambda P of U is equal to +1 means that in FP star, U is a square, because lambda P, after all, is a map from FP star to Z star and takes squares to 1 and non-squares to -1, right? So if lambda P of U is equal to +1, then it has to be a square in FP star, and that's what it means for it to be a root of this polynomial. Now, this is the polynomial f. What is f prime of x? It's non-zero. F prime here is going to be 2t. And x cannot vanish. I mean, x is not a root of 2t, because x is not equal to 0. So we can apply Hensel's lemma. This here must be Hensel's lemma with delta equal to 0 and n equal to 1. And so what is the conclusion going to be? The conclusion is going to be that there's a unique psi such that f of psi is equal to 0. F of psi equal to 0 means that it's a root of this polynomial, which means that u is equal to psi squared, and you get some other things as well. So psi is a square root of u. What is the summary? The summary is that if lambda p of u equal to 1, then u is equal to psi squared. This is what we have proved here. Okay. So that gives you the structure of this group. What is ZP star modulo squares? It's just equal to, it's a group consisting of just two elements. The image of 1, of course, and the image of u bar, where u is any unit which is such that lambda p of u is -1, which is not a square. Basically, that's what it amounts to saying. So, well, an F2 space is a vector space over the field F2. That just means that it's a commutative group killed by 2. And this here, as a vector space, it just equals, it's a space of all homomorphisms from ZP star to Z star, and it just consists of two elements, 1 and lambda P. Okay. So that was for P odd. Let's do it for 2 as well. When is a unit in Z2 star a square? So here a necessary and sufficient condition is that lambda 4 of U should be +1 and lambda 8 plus of U should also be equal to +1. And these two conditions are equal to U being congruent to 1 modulo 8. So another notation for that is that pi 3 of U, pi 3 of U is equal to 1. Right? Okay, so I have these this characterization of squares in ZP star and Z2 star. And this is, of course, also proved using Hensel's lemma, just as you look at this polynomial f equal to t squared minus u, and you take, so in order to apply Hensel's lemma, you have to start with an approximate root, right? So you just start with x equal to 1, for example. Then f prime of 1 is going to be 2. What is f prime here? F prime is 2t. So f prime of 1 is 2. And so the valuation Vp of f prime, p, it should not be p here. It should be 2. V2 of f prime of 1 is equal to 1, right? So that was called delta in the lemma. Delta is equal to 1, m is equal to 3, and so on. You apply your Hensel's lemma, and you get this. Okay. So now you see this space here, Z2 star modulo Z2 star squares can be identified with Z0 8Z star. Why? That's because, you know, the squares, that's because Z2 star squares is actually equal to 1 plus 8Z2. This was also called U3 in some earlier, right? So as an F2 space, it has a basis consisting of these two elements. I mean, it's what is sometimes called the Klein 4 group. It's isomorphic to Z mod 2 cross Z mod 2. But the difference is that, you know, when you write this Z mod 2 cross Z mod 2, you are thinking of, you are looking at an additive group. The group operation is addition, whereas here it's multiplication. It's a multiplicative group. I mean, they're isomorphic, but one is written additively and the other is written multiplicatively. And what is this little matrix here? It gives you the two, here are the two quadratic characters. And of course, these quadratic they are characters, they are homomorphisms. So in order to know a homomorphism, you need to know it's enough to know the values of that homomorphism on a basis of a vector space, right? And these two form a basis of this vector space. So this sort of gives you the values of these quadratic characters on these basis elements. Okay, so now we want to prove something, which is you have this projection by 1, which goes from ZP to FP, of course, right? It's, of course, a homomorphism of rings. of course, there cannot be a homomorphism of rings in the other direction. That's because this has characteristic P and this has characteristic 0. Right? So such a thing is not possible. But there happens, this pivot. There happens to be a natural section. Which is multiplicative. Multiplicative. So what does that mean? Section S, if actually the section is going to be called omega, so let me just use that notation. Omega. So what does multiplicative mean? Multiplicative means that omega of xy is going to be omega of x times omega of y. Okay, so let's construct this. Now I'm going to construct this section. So I define R to be the set of roots of this polynomial. T to the p minus t is a polynomial with coefficients in zp, and I'm calling R the set of roots of this polynomial. I hope this polynomial reminds you of something. Why is this chosen? This is chosen because you have x to the power p congruent to x mod p. This is for all x, right? This is what is called Fema's little theorem or something. So that's what the polynomial is, t to the p minus t. So I have this subset R of Zp, and I have this reduction map pi 1. So the claim is that pi 1 gives a bijection of R with Fp. And moreover, if I have two elements xy in R, then their product is also in R. And this omega, what is omega? Omega is the reciprocal bijection. If the pi 1 reduction modulo p gives a bijection here, you take the reciprocal bijection omega, and omega is multiplicative. That's the thing we are going to prove. Okay. So there we go. Now, f is this polynomial, and every a in fp is a simple root of f modulo p. That's immediately clear, right? Because, for example, I mean, there are exactly p roots, so every root is simple. It's a polynomial of degree p. Every element of fp is a root, so every root has to be a simple root. Otherwise, also you can look at its derivative and see what that a doesn't vanish at the derivative. So if it's a simple root, there has to be a unique root, which I call omega of a in Zp, which is congruent to a modulo p. This is what Hensel's lemma says. There's a unique root. This follows from Hensel's lemma. Okay, so now I have found, how many roots have I found? I found p roots. I found one root for every a in fp. So this R has at least p elements, and it can't have more than p elements because it's the set of roots of a polynomial of degree p. So R has exactly p elements, and therefore this omega, I mean this map reduction modulo p R to fp That's a bijection. And I take omega to be the reciprocal bijection. Now here is where I prove that this omega is bijective. Is not only bijective, but it's also multiplicative. Right? How do I show it? So first I show that if x and y are in R, then so is xy. So x is in R means that x to the power p is equal to x. Y is in R means that y to the power p is equal to y. Then these two things imply that xy to the power p is equal to xy, and therefore xy is in R, because R is the set of roots of this polynomial t to the power p minus t. Or in fact, this is not a, so what I should write is right? Okay, so I get this here. Right. So this R is called the set of multiplicative representatives of FP. And if I denote by R star the set of roots of t to the p minus 1 minus 1, minus, oh, why is it not? Minus 1, then that's just a notation. R star is the notation for this. Then R star and is in bijection. This pi 1 gives a bijection this way, and omega gives a bijection this way. And these are isomorphisms of groups. Okay. Okay. So in other words, I have this short exact sequence, and this omega, it should not go all the way there. It should go from here to here, here to here. Omega is a section of this map. This map is pi 1 here, right? Okay. So now let me skip this because that's not very interesting. Now what I want to show is that for every prime p, this zp star is the internal direct product of r star and u1. So what is the internal direct product? Let me just explain it for a commutative group. Let's say, suppose you have a commutative group M, and you have two subgroups G and H. Commutative group, and you have two subgroups. Then let's written additively, let's say. Then you have the subgroup G plus H, and you have the subgroup G intersection H, right? G plus H is the set of all sums little, so is a subgroup generated by G union H. And this is of course the intersection. So you say that M is the internal direct sum of G and H if this G plus H is actually equal to the whole of M, and this intersection is trivial. Now this was in the additive notation, but you can, of course, you have the analog in the multiplicative notation. So in the, if the notation had been multiplicative, G, why is it not working properly? This is not. Yeah, now it should work. Yeah. G and H, again subgroups of a group M, commutative group M, but written multiplicatively, then the condition is that GH should be equal to M. And of course, the second condition doesn't change, or it changes in this way. I mean, the intersection should be the trivial element. Okay, so now I have this group ZP star, and I have two subgroups R star and U1. Why is it the internal direct product of these two subgroups? Because first of all, I have to check two things: that the intersection is trivial, which is completely, yeah. Why is the intersection trivial? Because
These elements of R star are torsion, finite order.
yeah, they are going to be elements of finite order. So, well,
But elements of U1 are infinite order, of infinite order.
no, well, actually, there's some problem when P is equal to 2. This -1, for example, this is in Z2 star. It's of finite order, but it's not in R star. R star in this case will consist of just the element 1, and U1, I mean, this -1 will be in U1. Anyway, so the intersection is trivial because that's more or less by definition of R star, right? U1 consists of those elements which go to 1 under pi 1. So let me write it here. Suppose I want to show that R star intersection U1 is trivial. This is, I mean, this is more or less by definition. Suppose I have an element X in the intersection. Then X belongs to U1 implies that X is congruent. I mean, I should be saying that X goes to 1 in FP star. Let me put it this way. X belongs to R star. What is it? Means that X is equal to omega of whatever X goes to, X bar, let's say. So this, let's write X bar is equal to 1. So X is equal to omega of X bar, which means that X is equal to 1, because if omega bar, X bar is 1, then omega of X bar is also 1. Okay. So this is just by definition. And then you have to show that every element of ZP star can be written as a product of an element of R star and an element of U1. That's what this condition is here in the multiplicative notation. And this is the condition in the additive notation. So this is also absolutely obvious. I mean, you take X and you take W, you want to write X as W times U. We take W to be omega of pi 1 of X, and you just take U to be XW inverse. So this has to be in U1. Okay. So now let's go on to, there's this small lemma, which is used in many other places as well. It says that if I have a prime number P and some integer I, between 1 and p minus 1. I mean, different from p. 1 and p minus 1 inclusive. Then I have this binomial coefficient pi, which is of course p factorial divided by I factorial times p minus I factorial. What is being said is that it's divisible by p. Okay, so how do you prove this? This is very easy, because you have to show that it's divisible by p. And in fact, I'm going to show that it's divisible by p, not by p squared. In other words, I'm going to show that Vp of p factorial is equal to 1. No, Vp of p factorial is equal to 1, that's clear. That's because what is p factorial? It's p factorial is 1 times 2 times 3 times p, right? Now, none of these things up to here is divisible by p. This is the only thing divisible by p. So the power of p which divides p factorial is equal to 1, and that's what is written here. That's what is written here, that Vp of p factorial is 1. Vp of I factorial is 0 because I is strictly less than p. So p cannot divide I factorial, and it cannot divide p minus I factorial. And therefore, when I want to compute the Vp of this binomial coefficient, it is the Vp of p factorial minus the Vp of these two things. And the Vp of these two things is 0. So the Vp of this thing is also equal to 1. So p divides the binomial coefficient. Okay, so now I want to go on to show that, okay, yeah, this is the one that's interesting. So let's look at the case p different from 2. So if p is different from 2, you take your n to be any strictly positive integer, and if p is equal to 2, you take n to be strictly greater than 1. Then you have this mapping x going to x to the power p. The claim is that this mapping takes un into un plus 1. And so if it takes un into un plus 1, un to un plus 1, what will it take un plus 1 into? It will take un plus 1 into un plus 2. And what is being claimed is that, and this is included in this. So this diagram, of course, commutes. And therefore, this will induce a map from un modulo un plus 1. There's a thing on the left here, to un plus 1 modulo un plus 2. And the claim is that this mapping, this is an isomorphism. That's the claim, right? Okay. So first we have to show that if I have x in un, then x to the power p is in un plus 1. And if x is not in un plus 1, I mean x is in un but not in un plus 1, then x to the p is not in un plus 2. That's what we have to show. Okay. So x is in un, which means that x can be written as 1 plus p to the n plus a times a. X is 1 plus p to the n times a for some a in z, zp. So now I compute xp using the binomial coefficient, right? X to the power p is going to be 1 plus p to the n a to the power p. And the binomial theorem will give you that this can be written as 1 plus p times this thing plus a certain number of terms. And the last term is going to be the pth power of this, right? P to the np, a to the p. Okay, that's what the binomial theorem gives you. What are the terms here which I have suppressed? They are terms like No,
You
unmute.
keep it mute, otherwise echo will be there.